Well, hello everyone. This is I'm James Rickles, the PI and director of the NHERI Lehigh experimental facility, and I'd like to welcome you to our seminar series today. Where it may be tomorrow, but in any event, we're going to go ahead and proceed by Zoom, and we also have people here in person. The particular speaker we have today is Professor Nikos Markis. Let me introduce him first before I go through his title. Professor Markis, he's an internationally recognized expert in structural earthquake engineering and structural mechanics and dynamics. He's the NE family of Centennial Professor of Civil Engineering. He's from Southern Methodist University, that's located in Dallas, Texas. He received his PhD and Master of Science from the State University of New York at Buffalo, and holds a diploma in civil engineering from the National Technical University in Athens, Greece. Previously, he served on a couple of different universities of faculty, including the University of Notre Dame, University of California at Berkeley, the University of Patras in Greece, and the University of Central Florida. He's very active in publishing, has published more than 120 papers in technical archive journals. He's also supervised many students, including 14 PhD theses and more than 40 Master of Science and fifth-year diploma theses. He's served on various capacities in service, including being the editor of the Journal of Earthquakes and Structures, the associate editor as well for the Journal of Engineering Mechanics, ASCE. I'm sure many of you are familiar with that. And as a fellow of the American Society of Civil Engineers. In addition, he's a very busy person here. He's a distinguished visiting fellow of the Royal Academy of Engineering, that's in the UK, as well as a member of the Congress Committee and General Assembly of the International Association of Theoretical and Applied Mechanics. He's also won numerous awards, including the ASC James Cross Medal, as well as Walter Huber Medal, and the Side Award from the Institute of Civil Engineers in the UK, in addition to the Family Innovation Prize from ERI. Lastly, a career award from the National Science Foundation. The most important thing, including all those other things, is he's also served as a director of reconstruction of the Temple of Zeus in ancient Nemea. So let's go ahead and welcome Professor Markis. He's going to talk about the rocking isolation and effective strategy for limiting forces, permanent displacements, damage, and cost.
We're just going to take a quick second. Someone said that the audio was a little poor. I'm not sure.
Do I need to repeat myself?
No, you don't need to. I apologize. We're using
That's okay.
Test something for a moment, please. Okay, just make sure. Have to deal with.
Well, thank you, Professor Rickles, for this very kind introduction. Thanks everybody for coming to today's talk, either in person or remotely. It's a great pleasure to be here at Lehigh, visiting this beautiful uphill campus, together with these unique laboratory facilities. To enjoy a very pleasant introduction to the lab this morning. So thanks again to Yang and Tommy and all the people at the lab. So today's talk is on rocking isolation. And I will commence my talk with this way. Yes. So Tommy, the slides are advancing like this, right? So anyway, I'll commence my talk with this aerial view from the Carquinez Strait, which is slightly north of San Francisco, as we drive from San Francisco to Sacramento. And it shows in a rather convincing ways growing transportation needs of our society. So here you can see three bridges, a 1930 steel railway bridge that it's still around as a historic structure. 1962 bridge that for many decades was serving both the inbound and outbound traffic from San Francisco north. And a more recent bridge that was built now to serve the outbound traffic from San Francisco to Sacramento, whereas this 1962 bridge that had far exceeded its lifespan was kept in service because of some techniques that you have in structural engineering known as response modification strategies, was kept in service to serve the inbound traffic to San Francisco. How this was achieved? It was achieved with the technology of seismic isolation. So this is a closer view of this 1962 Venetian Martinez bridge. And isolation bearings, sliding isolation bearings, were placed between the piers and the deck of the bridge to limit the forces and eventually the shear forces that come to the foundation of overturning moments of these rather brittle piers. And in this way, by introducing this technology, it was were able to extend the lifespan of the bridge. And clearly, you see here that this technique of seismic isolation is a technique that serves these current concepts of sustainability, right? So this bridge was kept in service. Now, sliding bearings is not the only technology to achieve seismic isolation. Not very far away, some 40 miles south and to the west, there is another iconic bridge in the Bay Area. This is the Richmond San Rafael Bridge. And again, during the early 2000s, it was retrofitted with elastomeric bearings. So sliding bearings and elastomeric bearings are the two most prominent isolation bearings that we use for seismic isolation. Now, in addition to isolation bearings, we can also modify the response of structures with adding damping, and this is a fluid damper that one of the 94 fluid dampers that we tested for the retrofit of the Bay Bridge, and we'll talk a little bit about that. But what is most important to recognize is that these modern protection technologies consist of well-engineered devices that, when tested extensively and properly installed, I have it ready because it's very important, they lead to what we now call sustainable engineering. And I want to give a definition of this so that everybody is on the same page. Sustainable engineering is a design and construction of structures that meet acceptable performance levels at present and the years to come without compromising the ability of future generations to use them, maintain them, and benefit from them. So let's go to San Francisco. This is the Bay Bridge. You have here your back to San Francisco, looking to Yerba Buena Island. This is a suspended part of the Bay Bridge. And this in the early 2000s was retrofitted with 94 fluid dampers. This is one of them. These are big dampers, 400 capacity dampers. And few years after they were installed, less than 5 years, right before the
warranty of the damper expired, I was part of an inspection team to see the conditions, and to our surprise, all these dampers were experiencing appreciable leaking. The reason for the leaking that you can see here even more in a more dramatic way is because that whereas these dampers were designed for seismic loads, those who did the design did not account in their installation that the bridge will also move from traffic loading. So every time that an 18-wheeler was crossing the Bay Bridge was vibrating by these plus minus 2 inches that you see here. And because of this perpetual movement of the dampers, the end seals have essentially Teflon seals failed. And in less than 5 years, before even the warranty was expired, all of these dampers were essentially empty and they had to be removed. So here we have an example where in one of the most advanced communities of the United States, the Bay Area, and certainly one of the most advanced communities of the world, the damper sustainability was not achieved. So this was a motivation to do other things. So we decided to design a damper that instead of having oil inside, it has sand. And this is something that has been working for several years. So this is the first prototype damper that we built in Greece, actually. This is because it's before I moved back to the States. And so this is a view of the damper. This is how it was tested. So this is very similar to the setup you have in your small-scale testing facility. Here, the idea we mount the damper here, so the damper is cantilevered, and as explained to Professor Regis, in this way you will reduce the packing length, so the actuator essentially is pushing from here to here, right? So, and now, and of course, these are the force displacement loops that we report. So you see that the damper has this hysteretic behavior as the sand is compressed, you have this pinching effect. I shall say that something happened and we uploaded another version of this presentation. My student now at SMU Costas Calvas is working on a system design of this damper that we built here in the States under NSF funding to study various parameters in the design of the damper that we need to understand in order to be able to develop dimensional laws that will lead to optimal designs. So this is the seen in the response modification devices, but now I want to move beyond that to alternative ways of doing response modification strategies, right? So today I want to talk about rocking isolation, the basic concepts, application to valley bridges, and how these findings reinforced our ideas about retrofit of historic structures. So the motivation for developing rocky isolation can be introduced with this slide here, where I show one of the many bridges that were built in the late 90s in Greece. This is a valley bridge. And when you have valley bridge, you have very tall piers. So this bridge is seismic isolated, actually seismic isolated with sliding bearings. The coefficient of friction is only 5%. And even when you have a small coefficient of friction, because of the spans of the bridges are long of 60 meters, the weight that reaches that column is of the order of 30 meganewtons. So these bridges are like 14 meters wide. So every meter of a bridge weighs around 50 tons. So 50 tons times 60 meters is 300 meganewtons. And so the shear force is 5% of this force here is 1.5 meganewton. But if you apply 1.5 meganewton times the lever arm, you get this huge bending moment at the bottom that even with very deep pipe foundations, you cannot accommodate. You have to build caissons. So you go to this very expensive foundation design here, and this leads again to very expensive structures. So let's see if we can do something different. Now, in modern structural engineering, when we ask somebody to design a good frame, the first thing that comes in the mind of a good structural engineer is to design a statically indeterminate frame so that we have some redundancy, right? So static indeterminacy or redundancy is the first element in the design. The next one is that this element, this frame should be ductile, the connection should be ductile, right? So in order to dissipate energy during cyclic loading. And the next element of a good structure is that even after yielding, that this structure has always positive stiffness, so you avoid P delta effects. So redundancy, ductility, and positive stiffness are the three good things that we teach in the classroom for good structures, right? Now, ancient builders will do exactly the opposite. Instead of building statically indeterminate structures, they're building mechanisms. So a freestanding column is a one-hinge mechanism. Two freestanding columns with a rigid beam on top is a four-hinge mechanism, right? Now, to make things even worse, these structures, essentially they don't dissipate any energy. Energy dissipates only during impact, as these rocking structures alternate different points. And to make things even worse, these structures have negative stiffness. So what negative stiffness means? So let's go back to what positive stiffness means. Positive stiffness means that if I have a structure and I push it to a certain displacement, I need a certain force. If I want to push it to a larger displacement, I need a larger force, right? This is what this graph says, right? Negative stiffness means that if I have my structure and push it to a certain force, then if I want to keep it away from my equilibrium at a larger displacement, I need a lower force, right? This is what happens here. So these structures have negative stiffness, right? Now, so ancient builders would do exactly the opposite. Instead of having redundancy, ductility, positive stiffness, they're having mechanism, no damping, and negative stiffness. Yet these structures did exceedingly well through the centuries, right? They resisted the test of time, and actually these structures here, they prove that they meet the current design requirements, the most efficient design requirements, that they have, they can survive the earthquake that has only 2% probability of being exceeded in 50 years, and if you do the calculation, this gives a return period of 2.5 millennia, and this is exactly what is the case here. So these structures are indeed a triumph for sustainability, right? They have been around there forever, and if you know, without asking any maintenance, and the only thing that mankind did to these structures was to try to destroy them during various wars and other conflicts. So in order to understand why these structures are so, they behave so well and how they have so superior earthquake performance, let's study for a little bit the rocking response of the single column, of the solitary column, that is defined from its essentially its width, the height, and the intensity of the gravitational field. So, in other words, the ratio of the width over height gives a slenderness, right? And the size, we express it here with half diagonal, which is the square root of b squared plus h squared, right? So we have three things, either width, height, and g, or size, slenderness, and g. So, in a similar way that a single degree of freedom oscillator is defined by stiffness, damping, and mass, right? A rocking structure, a rocking column is defined by width, height, and G. Right? These are the three things. And they look similar, but they are very different, right? And for instance, we already stressed out that the stiffness away from equilibrium in the harmonic oscillator is positive, whereas in the rocking column is negative. Another element that is very important is that the restoring mechanism in a harmonic oscillator is the elasticity from the spring, whereas the restoring force from in the rocking structure comes from gravity. Now, the stability of top slender structure, of course, was well known from the ancient times through the construction of these emblematic temples. But the first person who really uncovered its dynamics was George Housner back in the early 60s at Caltech, where he showed that among two freestanding rocking columns that have the same slenderness, which means that have the same aspect ratio, the same width over size, right? The taller one is more stable. So he brought forward as a size effect, right? There is a size effect. So what essentially he showed in his paper, he showed that the larger of two geometrically similar blocks can survive the excitation that will top the smaller block. And he plotted these results in this way. So in here, alpha is a slenderness. Actually, a better way to have it here is tangent alpha, but when alpha is small, tangent alpha is equal to alpha, dividing, no, I'm sorry, A is the acceleration of the pulse here, A on the numerator, and G alpha or G tan alpha is the acceleration that you need to create uplift. So in this vertical axis, you have how much acceleration you need to overturn the column compared to how much acceleration you need to uplift the column, right? So the column will uplift when the force here is equal to tan alpha, right? G tan alpha. But he showed here that as the size of the blocks or the columns increases, so what is this P here? This P here is the square root of G over R. So when R is bigger, R will go to bigger columns, this P becomes smaller. Omega is the frequency of the excitation. So when the size of the column increases, this ratio increases. And he showed that there's a big margin between the acceleration you need to create overturning compared to the acceleration you need to create uplifting, right? And this is why tall structures, big structures, they have this extra stability compared to smaller structures that they have the same aspect ratio. Okay, so one can write the equation of motions. I don't want you to understand everything. So you have two equations, one for positive rotations, one for negative rotations, and you can combine this by using the signum function, a generalist function. So all I want you to remember is that the angular acceleration is equal to this p squared, the p is the frequency parameter that I said that as the size of the column increases, p decreases, right? Times something. So even without solving this equation, it tells that when you have a bigger structure, p is going to be small. So in a bigger structure, the angular acceleration is going to be smaller, right? Now, I want you to remember this because I'm going to use this later on. Let me skip this. Now, George Housner, in order to create this the overturning spectrum that I showed you earlier, he used a half sine pulse. Now, half sine pulses do not exist in nature. What we have ground motions, but some of them they have these coherent pulses here, and these are some of the mathematical pulses that capture very, very well the coherent component of strong ground motions. So we derive in a similar way that Housner derived the overturning spectrum for a half acceleration pulse. We derive now this for these physically realized pulses, and the result is this one here. So again, we plot the results in terms of the dimensionless term. So here is the overturning the acceleration of the pulse that is needed to create overturning compared to the acceleration that needs to create uplifting. And you see that regardless if this is a one-sign pulse, if this is what we call a Ricker wavelet of this symmetric Ricker wavelet, or if you have an antisymmetric Ricker wavelet, we have the same trend that as the size of the block increases, you need a way bigger acceleration to create overturn. And this increase is very dramatic. So, whereas here, of course, when the block is very small, upon uplift is overturns, right? There is no any safety. But when omega p over p lane, let's say is on the order of 8, you get a 10-fold increase. So it will uplift, but then you need 10 times that acceleration to create overturning. So we can enjoy this huge dynamic stability in our design. Okay, so I'm going to explain to you why this dynamic stability, from when this happens. So let's do what people were doing until very recently, when they were trying to find the stability of these freestanding structures. They were using what the code says to do an equivalent static lateral force analysis. So as the earthquake moves towards, in my side, it goes to the right, the column is going to uplift, and so this is the D'Alembert force that is pushing the force, that's trying to uplift the force. And if you take moments above this point, you have that the demand is this force times this lever arm, right? MUG times H, and the capacity is the weight that is this force times the lever arm here, right? And if you divide by the mass, you get that the uplift acceleration is g tan alpha, but this calculation will tell you that also this will be the overturning acceleration, right? Because we don't take account of anything else. But this is not a static problem. This is a truly dynamic problem. And this is where the confusion was there for many years. So if you do the dynamic equilibrium of this, you have again, the demand is mu ground times the height. Now I take a slight rotation, so the projection is cosine alpha minus theta. Then you have again the restoring force from the weight, which is mg times the width, alpha sine theta, alpha minus theta. But then, because this now is trying to uplift dynamically, you have to account here also what? The inertia forces, the contribution from what we call the mobilization of the rotational inertia, right? It's a dynamic. It's like, let's say you have F equal ma, here you have iota theta W dot equals sum of the moments. And in every object, no matter what is the geometry of the object, the moment of inertia proportional to the square of the size, right? Proportional to the square of the size. So in other words, if you want to do a moment balance equation, you have the seismic demand. So the overturning moment is proportional to the size, but the restoring the capacity that comes from this dynamic term is proportional to R squared. So simply stated, Housner's size effect is nothing else but that eventually a quadratic term with this term here eventually dominates over a linear term. Right? This is the dynamic stability problem. So you have here the size of the column. This is seismic demand is a linear function. This is the seismic capacity that comes mainly from the defeat to mobilize the rotational inertia. And eventually the seismic capacity will always be greater. So in the book, whenever you see something interesting, I also show the papers where we have published these results. Okay. Now, I want to move to something more practical. In life, when we have big tanks or when we build bridges, we don't have like a solitary column, but we have array of columns coupled with a rigid beam, right? Would be columns coupled with a deck. So I want to find the dynamics of this system here, which is what is this? This is an array. It's an array of freestanding columns of the same slenderness, same size, which are capped with a rigid beam. Okay. Now, this is a single degree of freedom structure, but it's a difficult freedom, difficult simple degree of a single degree of freedom structure, because we have too many unknowns. So the degree of freedom is theta, right? So each column rotates by the same amount. The horizontal displacement, the vertical displacement can be expressed in terms of the rotation theta. You can solve this problem with in two ways. Either you can use a direct approach, what we call a Newton's law, right? The flight equal main. But you can solve this only if you have only two columns. You can do this only when you have two columns, because you need to calculate these internal forces that are between the top of the columns and the bottom of the cap. If you have more than two columns, you have too many unknowns you cannot solve. But you have an alternative way of solving things in dynamics, to use Lagrangian dynamics. It's an indirect approach which says that what it says essentially says that among all geometrically admissible paths that a structure would go from point A to point B, the true path that is going to happen is the path that along this path the difference between the kinetic energy and the potential energy is minimized. Okay, and by doing this in dynamics, you get what's called the Euler-Lagrange equation, and then you can solve. So this is what I said before, that the horizontal and vertical displacement are related to the rotation theta. These are the velocities. So it's a single degree of freedom structure, right? A single degree of freedom. And by following the Lagrangian formulation, because you have more than two columns, right? So when you have a bridge, you have more than two piers. This is the equation: T is the kinetic energy, theta is the rotation, theta dot is the angular velocity. So the kinetic energy is very easy to calculate. Q is what we call the generalized forces. W is the work. And when you follow this Lagrangian approach, you find the solution. The solution is that the angular acceleration is something else that multiplies p squared, we saw this before, times exactly the same thing that appears in the solitary column. So this is a very interesting result, because this ratio gamma is nothing else than the mass of the beam divided by the mass of all the columns, right? So this quantity gamma is always positive, right? It's a ratio of two masses. The mass of the cap beam of that system divided to the mass of all the columns. So this ratio, 1 plus 2 gamma divided by 1 plus 3 gamma, is always smaller than 1. So by being smaller than 1, it says that the angular acceleration of the rocking frame, what I call now, is equal to what happens to the solitary column, because P is the frequency parameter of the solitary column, times by this quantity smaller than 1. So it corresponds to an even smaller apparent frequency parameter. So this is even more stable. So what we find here is that the equation of motion of the rocking frame indicates that the heavier cap beam is, the more stable is the freestanding rocking frame, despite the range of the center of gravity. And let me show you this schematically. So this equation says that the dynamics of this system here, where you have an array of columns of slenderness alpha and size r, capped with a beam with mass b, is identical, is mathematically identical to the dynamics of a solitary column of the same slenderness alpha, but with bigger size. But if you have bigger size, you have a more stable. So this column here is more stable than this column. So that system here is more stable than this individual column, right? So these are great news for seismic protection. So let's summarize what we have shown here. So we knew already from George Housner that among two geometrically similar columns, the bigger one is more stable compared to the smaller one. And then what we have showed, and these are the papers that have showed these things, is when you take two of these columns and you cap them with a rigid beam, this system is more stable than that. Because this system here corresponds to a column of the same slenderness but larger size. But then if you increase the mass of the beam, that 1 plus 2 gamma divided by 1 plus 2 gamma increases asymptotically in 1.5. And you increase the mass of the cap beam, this becomes even more stable, which is actually counterintuitive, right? But this is what the equations show, and this is what we have to accept. So this is great news for many things. So we publish this paper, our top heavy structure more stable. And this is something that, for instance, was great news for reconstruction. As Professor Ricky said, I was involved in the reconstruction of an ancient Greek temple, this is the temple of Zeus in Lehigh, Greece. They're all three standing columns from the ancient times. And we embarked in this 7-year project to reconstruct this northeast corner. You see here how badly was damaged the foundation of the only one column remaining still from the ancient times on the base side of the temple. These are the fillings that were created to fill up the broken pieces. And this person here is the person standing in front of you in younger. So we have reached that point. We have reconstructed the northeast corner. So remember, these are the these 2-3 dark columns. The only one remaining standing from the ancient times, and these two, the darker columns, are those that are remaining standing from the ancient times. And you have reconstructed the northeast corner. And there's a question if we had to place atop the epistyles. But now we knew that by making the top, by putting the epistyles, which are top heavy, that this is going to be even more stable. And how we know this? We know this from this guy, from Lagrange, right? By Lagrangian mechanics. So they had a very convincing argument to put this on top. So this is what, from where we started, and this is how we reconstructed the northeast corner, and this is the end product of our effort. Now, this is something that is not a secret. Nature knows this very well. So this is another evidence that when you have a rocking frame, it's something very stable. This is the top of bell tower in Italy. So it's a top bell tower. And of course, this was made out of masonry. It's a very pretty tower. And when you have the Gaio earthquake that happened in 2008, this brittle tower failed. And by generating these 4 hinges, this became a rocking frame. And this structure, by converting itself to a rocking frame, survived the earthquake. So, of course, this idea is also great news for bridge engineering, because you know now that if we let things roll, the heavier is the deck, the more stable is the structure. We have been working a lot on this, and the idea is that at some point in structural engineering, when we build bridges with tall piers, we have to disentangle at some point from capacity design, where we bring all this reinforcement and move on to this concept of articulated structures, which lead to very stable structures because of their ability to move. And this was not a secret. It was implemented in New Zealand with the South Rangitikei Bridge. And the reason that it was implemented is because these bridge piers are so tall that any other solution is not feasible. So the overturning moments here at the base of this bridge were so large that no pipe foundation could be designed to take these huge forces. So the engineers then decided to make these piers freestanding. This is called at that time a stepping bridge. And this bridge is capable to step on its legs. it was truly innovative design. You know, this was almost 73-meter tall, and it was indeed a seminal moment in earthquake engineering and in designing seismic resistant structures. One thing that I should say here is that whereas these foundations were not planned to uplift, these piers were equipped with a primitive damper. This was at that time a torsional yield damper. So imagine that these two, so you have a tubular section that these two ends are fixed and you move up and down the middle one. So these tubular sections are subject to torsion. This is essentially a torsional yielding beam damper, and the whole design was very nicely balanced, and we went through series of calculations that now that we understand these mechanics very well, and we found out that this bridge not only is able to survive the strongest earthquake known at the time that this bridge was designed. So this is the response of the bridge because of the central record, and this is the response of the bridge because of the powerful California earthquake. And so this is the uplift of the piers. The uplift of piers is few centimeters, right? These dampers had a stopper at 12.5 centimeters. So even with this El Centro earthquake or the part of the earthquake, the uplift of the bridge was below the threshold that the engineers have put at that time. But even if the bridge is exposed to stronger earthquakes, like the Tacoma Dam record that happened during the design of the bridge in California, I remind to the audience that the Tacoma Dam record, or I should say, a newly completed hospital, not very far away from where the Tacoma Dam record was recorded, totally failed because of a soft-story failure. The uplift of the piers of the bridge still remain below the 12.5 centimeters, which was the threshold that was assigned by the design engineers. So this is a very interesting situation, whereas a structure that was designed with capacity design failed under this record, our local structure still operates under its serviceability state, right? I'm going to move on. I have some other response analysis of this bridge, but I want to move to the seismic protection of buildings with rocky walls, partly because you have one of these experimental setups here in your lab. And of course, the challenge in earthquake engineering is to reduce soft-story failures, some of them which happen at mid-height, right? So this is well known, and one way to do this is by coupling a moment-resisting frame with a core wall. But when you have a fixed base core wall, these core walls are going to attract a lot of forces and moments at their base. So one way is to have this wall rocking, or in some application in Japan, they have a situation when this rocking wall was spinning. Let me go through some of the challenges of tall buildings with shear walls. When you have a fixed base shear wall, you have larger activity demands under near-fall pulses, cyclic degradation, residual drift, and large repair costs, right? So when you have these inelastic deformations, you may achieve the structure to not collapse, but your residual drifts, what you call now functional recovery, is the residual drifts are so large that essentially you have to demolish everything. So these are unsustainable part of the practice. So what what we can do? We can do something that is not new, right? So the idea of having rocking walls in bridges goes all the way back to the work of Nick in 1978, who has published this paper, actually has also foreseen the need to have the moment resisting frame somehow articulate to the wall with this kind of links, right? Some of the ideas that you can see now in your lab. The same ideas were brought forward much later by John Mander and his team, where again these articulations happen now by creating well-thought plastic hinges. And again, this idea, as I said, of the rocking wall, this is a pin rocking wall, was implemented in Japan by Professor Wada and his team by installing these 6 rocking walls in this 12-story structure. So these walls essentially just ensure uniform distribution. You don't have any resettling from the way because these walls here are big, right? So advantages of stepping rocking walls. So if the rocking wall is also stepping rocking wall, so it steps by its 2 corners, you can accommodate large displacements while remaining serviceable, immediately following a strong ground motion, control deformation, minimum permanent deformations because the weight of the wall tends to recenter the whole structure, even if the structure has behaved inelastically. And it is indeed a practical alternative to capacity design. We have done extensive analysis to see what would be the potential benefits by adding vertical tendons in rocking walls. The answer is that as you go to larger structures and larger rocking walls, the contribution of vertical tendons is marginal. The weight of the wall does most of the job. I have all this in papers that the only thing that vertical tendons do, and I have it here, they increase a lot the reaction force at the pivot points. We have seen here in your lab that some of these cross-laminated timber suffers from this reaction force at the corners. So by creating a tendon, essentially when even in the case when the wall is bigger, the only thing you do is you increase even more the reaction force without any change in the response of the drifts. So the conclusion is when you go to tall structures, tall walls, no need for vertical tendons. And I will move on because I'm running out of time. We did some so these are results for the tendons. I want to move now to my conclusions. So what are the conclusions? So the main conclusion is that rocking isolation is a truly dynamic sizing protection strategy. So you cannot design buildings where elements rock by using the equivalent static lateral force. So you have it's a truly dynamic phenomenon. So it's a dynamic sizing protection strategy where most of the sizing resistance when you have freestanding columns or walls originates from the difficulty to mobilize the rotational inertia. These are the results that were brought forward by George Housner and Caltech that among 2 freestanding columns of the same size, of the same slenderness but different size, the taller one is more stable. And then the findings of our studies. So let me see if I can play this. So this is 5 degrees. We had a small design office. So let's see here. Here this is like much younger, right? So this is the first conclusion that the solitary column here, and this is 2 solitary columns with a rocking frame. Okay, I'm going to take here that was very, to achieve this was very delicate, but this is what we say that the rocking frame is more stable than the solitary column, right? Top and heavy structures are more stable, right? Remember this. And the next answer, the next conclusion is that if you have two rolling frames, because you can see the trend, when you have two rolling frames, one has one cap here, here cap B, everything is freestanding. So this is my hand-driven shift technique that I designed among two rolling structures where top end is overstaying, right?
You stopped it too soon. So you stopped it too soon. You need to see the collapse. I'm only kidding.
Okay, it's going to collapse. Okay, so let's go to. Okay, we talk about also the conclusions for the rocking wall buildings. So let's finish my presentation with this this lithography from the foothills of the Acropolis in Athens, right? So in the foothills of the Acropolis, there are these extremely slender and tall columns, very slender, right? Very tall. And they have been standing there all alone for millennia, right? Whereas Athens has experienced many earthquakes that have destroyed buildings, highly rise buildings, factories, buildings that have been well engineered with the modern knowledge of capacity design. So these columns here, there is no any connection, no any reinforcement, no any ductile design, nothing. The only reason that these two solitary freestanding columns remain standing for more than 2.5 millennia is not because of any ductile connections or continuation of steel reinforcement, but because while they are very slender, they are tall enough to survive through the centuries intense shaking that has damaged repeatedly the well-engineered structures in the city of Athens. So this is the last slide of my presentation that shows the adventure of the rocking frame through the centuries. It started with this very clean design, right? Then we have the evidence from nature that rocking structures can survive very violent earthquakes. These ideas have been forgotten for decades now. Our thinking when we go to tall bridges remains entrenched in capacity design. However, there have been ideas to move away from that. I would like to mention this concept of damage avoidance design that is proposed by John Major. But now we have shown that when these columns are large, you can even avoid this vertical post-tensioning and go to totally freestanding rocking structures. So with that, I want to finish my presentation and thank you. This is a photograph of these two very slender columns that remain still standing. Thank you very much.
We have some questions. Okay. We'll start with, there's a few coming in.
Okay.
And I'm gonna just start and then we'll wait for the audience. You didn't come first. I'm only kidding. We'll get to you. Sorry. So let's just read them here. We'll go for the chat first because that's the first one that came in. What should be considered as the safe point for design on moment rotation plot for this controlled rocking frame? So that was earlier. This one here. That was earlier in the presentation.
What should we consider? Okay, so let's remember what we say. So these columns have slenderness. They have slenderness alpha, and we showed that even when you have strong earthquakes, if your column is tall enough, the uplift and the overall rotation is a small fraction of alpha of the slenderness. So maybe I should go back here. Huh? No, I should go here so I can go very fast to answer this question. So I have here the South Ragidike Bridge. So I'll start with this. Okay, so I'll go here. So these columns have they're very tall because of the railway track. The center of gravity is elevated, so the center of gravity is here. This is the slenderness. The slenderness is only tan alpha is 8.37 degrees. So G tan alpha, so tan alpha is this 0.14. So whenever you have a horizontal, it's very important to understand this. whenever you have a horizontal acceleration greater than 0.14 G, which is a very weak earthquake, right? 0.14 G, these columns are going to uplift. They uplift, right? But because they are so large, the earthquake is able to uplift, but is not able to mobilize the rotational inertia. This is what is very important for us to understand, right? And so while these columns are very slender, then if I go to my next plot here, we see that here we have a rotation. So the rotation from the biggest rotation is only 6% of this slenderness. So when these columns are subjected to the central earthquake, they only uplift what? 6% of the slenderness. Now you go here to something that is let me see, make sure I have this result. They rock 6%. Let me see, this is theta stop, right? Okay, so the theta stop here, where you have these restrainers, is 6% of the slenderness, and yet when this structure is subject to the earthquakes, go to a fraction of that tolerance, and even if this is a stronger earthquake, you go to, let's say, to a third of the 6%. So this is the idea that the rotations are very small. They are very fractional to the slenderness. Of course, when the column go to its slenderness, then you are the version of overturning, but you are so far away. Even when you go to Pacomara dam record, here you barely reach this 6% of the slenderness. And when you go, let's say, to the Essex and Turkey record, you exceed that, but this is again less than 10% of the slenderness, 0.1. So the answer is that when you go to, of course, if you go to smaller structures, to smaller columns, then you have bigger percentage of the slenderness, and this is something that needs to come out from the calculation. What is the other question?
Well, we'll ask our esteemed audience member here. So thank you very much for the presentation. You've combined two of my favorite things, which is ancient Greek buildings and structures. But I had a little bit of a comment that I was hoping that you could maybe talk about a little bit more. Is that one of the things that we've seen in some of the modern buildings, it escapes me the name of the building out in San Francisco, but they did this performance-based seismic code, constructed building. But after they got it up, the occupants had a lot of discomfort because of wind loading. There was a lot of acceleration.
Okay.
And typically you see that balance between wind loading being, requiring a heavy roof and seismic requiring a light roof. And with the things that you're saying in this, like you don't need to do one or the other. You can combine those two things together and optimize under both. So if you could talk a little bit
Okay, I want to comment about this because these are extremely interesting questions. Okay, so all this analysis that I have presented here, and this is a good approximation, is for the case where the rocking element is rigid, right? It's rigid, and this is true for an ancient Greek column. So ancient Greek columns are more or less around 11 meters tall, 11 meters. So 35 feet, right? And the aspect ratio is usually 1/6, and so between 1/6 and over 7, right? Okay, so we have done analysis up to buildings of, my former PhD student used the 9-story SAC building as a vehicle for analyzing the benefits of rocking structures. And again, the concept of a rigid wall up to, let's say, 9 or even 12-story structures by having a slenderness of about 1/6, right? So you have, if you have, let's say, a 10-story structure, it will have, again, 35 meters. So let's say 36 meters, 1/6, your wall will be 6 meters wide, right? So 6 meters wide, 36 meters tall, right? And this is a good assumption for a rigid assumption. If you go now to a taller building, right, or you cannot have such a wide wall, you have to go to slenderness that are less than 1/6, like 1/7. Now, if you go to two slender structures, then maybe this rigid wall is not anymore, this assumption of a rigid wall is not anymore valid, right? So the wall will uplift, but also will flex, as was shown in the paper by, let me go here, right? So the wall uplifts, but also flexes, right? So when you go to tall buildings that suffer from wind vibrations, you need to do some more calculations, right? But what the message that I want to convey today is that by having something, by building an articulate structure, or by having something that's allowed to rock, you bring to the structure extra beneficial forces, which are from the difficulty to mobilize the rotational inertia. So by allowing something to rock, you introduce to the structure big elements that tend to rotate. And when something tends to rotate, it has to mobilize the rotational inertia. And this is an enormous effort from the earthquake that at the end gives up. So this is this dynamic stability. The earthquake can uplift something that is slender, but it is impossible for this earthquake to overturn it if it is big enough. So big enough, something big square is even more bigger. This is the idea. I don't know if I answered your question.
No, that was nice. But a follow up with that, if you're allowing it to rock, have you looked at what kind of detailing needs to happen at the corners? I mean, you're getting.
Okay, so this is an excellent point. So do you want to start with the ancient builders, what they're doing? And then you can see what they, so, okay. So for a general answer is that this is a fascinating area for high performance concrete, for clever ways of reinforcing the corners. You have like ordinary concrete. Maybe you can, if you have a rocking wall, you can manufacture a steel shoe that the steel shoe is going to rock around and to remove these concentrated forces. But let me spend a few minutes to say what ancients are doing, right? Because ancients are not building. I have like 2 minutes to say this because this is very interesting.
Take all the time you need. No, it's not.
So ancients were building. So the Parthenon, for example, is made of a very high class material. It's made out of this very high quality marble, right? Which has an amazing strength. I mean, it has the marble of Parthenon has a compressive strength between 40 and 50 megapascals, 2 times the strength of concrete, right? But there are temples in Greece that are built out of limestone. And the temples of limestone has a compressive strength of 5 megapascals, a quarter of concrete, right? So they knew that when their columns are going to uplift, the columns are going to get damaged, right? So they're creating intentional fuses. So what are these intentional fuses? I don't know if you have seen these columns. Maybe I have them at the beginning of my, I don't know if I can do this. Yeah, so you can see these flutes here, right? You can see these flutes. So almost everybody thinks that these flutes are just architectural elements. Well, it is very pretty because, in Greece you have this nice sun, and the sun comes and it gets deflected, and it creates a very like pale image of the temple. So it's really beautiful. But it has also other purposes. So each column has 20 flutes, right? And these flutes were carved in the marble, and then they were they're installing also what's the word? Artificial stone to make them even look better, like grout, like we use grout, right? They're grouting them with to make them even better, right? So they knew even before they were getting damaged, they had this grouting technology to make them look even nicer, right? So this protruding corner, so imagine that when you have these flutes, you have these protruding corners at the base. So when the column was uplifting, these corners were immediately cracking. But these are like very concentrated points. By having these points cracking, you're creating a finite distance where the column could rock, right? And so they're intentionally yielding the location where the column is going to rock by creating a finite surface. And then after the earthquake, they're repairing it with grout. And also, I think this is my interpretation, by having these flutes, during the first uplifting, you had this cracking, this yielding, they're creating the first intentional axis of rotation. And somehow they're guiding the whole system to rock in a planar motion rather to rock. So if you have a bottle that's a cylinder and you uplift, it's going to walk also. So by having these flutes, you are uplifting and then you're creating the sides of a polygon. And then the column was forced to rock along the sides of the polygon to avoid this kind of walking. It was a very, this is my interpretation because I have done a lot of experiments in rocking. But every time you do in a cylinder, you have this wobbling. Whereas by this, they're intentionally creating the size of a polygon, and then the column is rocking only in a planar motion. So maybe one time when I retire, I write a book on these things.
Thank you.
I don't know if I gave you a satisfactory
Yeah, I
answer.
like it.
Wonderful, thank you.
So we're gonna keep going as long as you're okay with.
Oh, I'm totally okay.
It's like the audience can stay.
I
do whatever they
had
want.
so many slides that I skipped
We
because
have plenty of time here. We'll
Okay.
keep going. Thank you for your wonderful presentation from Mr. Anonymous. And you did some research in the past on restrain. Is that restrain or restrain?
restraint rocking bridges.
Okay, I
Yes.
missed it. Okay, rock and bridge bent with restrained with PT and free rock and frame. So
Yes.
you think post tension tendons are beneficial for bridge
Yes,
columns?
yes, they are. Okay, so again, when you have, let's say, an overpass, where the height of the overpass is, let's say, 10 meters, like 30 feet or 35 feet, so the column is big, but not very, very big, you may need to have some post tensioning, but you should not kill it. I mean, the tendons should have a finite stiffness so that it does not hold down the column to the extent that the column cannot uplift. And this is the ideas of John Mander in damage avoidance design. Of course, if you have medium size, and I have some results here, if you have medium size columns, let me see. Yeah, I can explain it, don't worry. But if you go to very large columns, to very large valley bridges, like the one I showed, the valley bridge in Greece, you have 60 meters. Once these columns start to rotate, the recentering from the difficulty to mobilize the relational inertia is so huge that is overriding any restoring force from a tendon. So when you go to big bridge piers, like let's say 20-meter tons or 30-meter tons, then the effect of the restrainers is marginal. You can totally avoid them. So smaller bridge piers used to apply vertical post tensioning. Bigger bridge piers you should let it go because of the square effect, right? Let's go to another.
Let's do the last chat from Khalid here. Is size, frequency, scale, effect, shape dependent? For example, circular cross section versus rectangular.
No, so the size effect is independent of the cross section of the column. It goes only with the vertical size of the column. So it's independent of the cross section.
Okay. All right, next question. Utilizing energy dissipation, sacrificial elements are advantageous for rock and frames or not? Those rock and frames will no longer then exhibit negative stiffness while incorporating energy dissipators and post tensions. They will show positive post uplift response as opposed to the freestanding columns. What do you think?
Okay, I think I think I have a. All right, so maybe this will answer this question. So here I have a 6 degree of freedom. Can I use this?
Let me make sure.
Yeah, I can. So I have a single degree of freedom that is covered with a rocking wall. And why this is a good approximation for multi-story buildings? Because the rocking wall, as the building vibrates, it will, by definition, induce a first mode dominating response. Because of the rock of the rigid wall, the building is forced to a first mode response, right? So this simple model is very adequate for this kind of systems. So this is how we analyze this moment resisting frame, yielding moment resisting frames with rocking walls. And this is the case where the wall is vertically restrained. So in the absence of the vertical tendon, the moment rotation curve is this one here when you have the negative stiffness, right? So you need some moment to uplift, and then as you go here, you have negative stiffness, and then you have right. Now, if you put a weak tendon here, a tendon means that has small EI, you raise its stiffness, but this EI can be still weak enough to enjoy this negative stiffness. Now, if you make if this tendon becomes stiffer and stiffer, you increase this behavior, and you end up having what you used to have in elastic structures, a rigid elastic behavior, right? So by having a very strong tendon, or by increasing the strength of the tendon, you go away from the properties for the dynamics of rocking. Still, now you have this positive stiffness, but still in this case, you enjoy your centering from the weight. The problem is that in this case here, I want to show this result here. So this is a response of a building. So the dark line is without tendon, with rocking wall. And there are two lines, one with a weak tendon and one with a very strong tendon.
Just highlight.
Yeah,
People that can't see your highlighter.
Yes.
Top left.
So the effect of the tendon in this case, because it's a six-story building, is very marginal. The only bad thing that the tendons do, as I said, is they increase a lot the reaction at the pivoting corner. So in this case, it's clear that you should not put a tendon. I don't know if this is answered the question, but let me.
One last question.
Yeah.
We have, if any other ones want to come in, we might have, looks like this is our last one for now. What type of damping someone should consider while analyzing rock and column? For traditional design, we consider railing damping, but here it seems like the rock and column experiences some impact. Any idea what special things we need to consider while designing a rock and column in practice?
Yeah, I shall say that when you go to this kind of systems, these are like totally nonlinear systems. One should go away from railing damping. One should do a full nonlinear dynamic analysis and use the well-known models we have, like the Bookwen model. It is embedded in OpenSeas, or other models that capture exactly what is happening by averaging the effects of damping through the structure. You are going to lose a lot of the very interesting things that happen because of the nonlinearities. Sometimes nonlinearities, while you don't like them, are very beneficial in the response of structures, and we take advantage of them. So we should not hide them. Thank you very much.
Yeah, hold on.
Okay, yeah.
So, Cassius is hungry. Sorry, you're already starting to clap. You must get.
Yeah.
So I see the mitigation from the rocking wall. So most of it is coming from the impact to dissipate energy, or because you're changing the frequency of the structures, you shift the frequency.
All right. So I'll tell you the good things about why coupling a structure with a rocking wall. Why? The first and most important is we don't want to have a mid-story failure. And in Cobb earthquake, we had a lot of things like this. You don't want to have this, right? So you say, okay, the first thing I want to have is to have a uniform drift distribution. I want to avoid this, right? Right. So this is already a very good thing. Now, the other thing is that when you have this So this structure here, I don't know, it has a 10-story. If you put a wall with slenderness 1/6 or 1/7, you will have a weight of 7 meters, let's say. So when this huge thing uplifts, it has weight, right? So even if this structure deforms in its moment-resisting connection inelastically, and you have permanent displacement, this heavy wall is going to recenter the structure. So far, there is nothing about damping. The first thing is uniform drift distribution. The second thing is that you want, what is the most important trend now? Functional recovery. So rocking walls is the best avenue to that, right? To recenter the structure and reduce or perhaps eliminate permanent displacement. Okay. Now you have to go one step further and to say, okay, how about if I also put some damping, right? So there are many ways you can put damping. But perhaps the most interesting way to put damping is this. So let's say that this is your rocking wall. So you can either put vertical dampers here, like this damper that you are testing, fluid dampers, or perhaps you can put buckling restraint braces in elastic, yielding dampers, right? Now, again, the same story. If your structure is not very big and your wall is not very big, the effect of these things are going to be noticeable and you are going to benefit. But if you go to a very big structure where this wall is very big and very heavy, the effect of these things is going to be unnoticeable, right? And you have to do the calculations, but these are the things that we have observed. We have observed them. So far, we have done only planar motion of these frames. So I think the next step is to go to a truly three-dimensional analysis, like you do here in your test. You do bidirectional testing and reassess all these findings. But at the end, I think that this scale effect, the scale effect that when you go to bigger structures, the effect by setting something in rotation, you mobilize the rotational inertia, the rotational inertia goes to the square of the size, and this overrides every other effect.
Any follow-up?
Okay. You mentioned leaking dampers. What was the cause of that again? Was it just wear in that small?
On wear of the end seals.
On the, I guess.
From the perpetual traffic loading, Jim. So every day and night, as 18-wheelers would go through the bridge, the Bay Bridge was vibrating. You know what period? 10 seconds. You cannot feel it, but it was vibrating. So this perpetual motion weared out the end seals of the dampers.
The seals actually wore out.
Yeah. So now, so one way of avoiding this is to lock the damper with some fuses, so they don't vibrate during traffic loading, and when during the big earthquake, these fuses are going to give. And so this is one way to do this, but it was not done at that time. So if I can say one last thing, I want you to leave this room by remembering that the seismic protection, because of, especially in freestanding rocky structure like columns and frames, comes from dynamics. It's a phenomenon where motion creates stability, right? Motion creates stability. The ability that these structures are able to move, they are able to rotate. By being able to rotate, they tend to mobilize the rotational inertia and they become stable. It's the same way that when you are in a bicycle and you go, you are moving, you are stable because of the what? Because you enjoy the what? The angular momentum from the wheels of the bicycle. And when you stop, you can no longer maintain equilibrium, you have to beat your foot on the ground. So the same way that when you're on a bicycle, motion creates stability, the same thing is why ancient Greek temples survived for 2.5 millennia. More motion creates stability. Thank you very much.
Thank you, everyone. And then if anyone wants to contact you personally, is it okay?
Oh, it's totally okay. So here I have the presentation. At the bottom, I have papers that reference to the slides. So I'll take the liberty to mail the papers to you and Yang,
Okay.
so people can have access to
Absolutely, and we will make that public on the Design Safe Lehigh webpage
Excellent.
in the coming weeks or so. We appreciate your time here
Thank you very
and
much
doing
for the
that.
invitation.
And for all the audience members, thank you for joining us. We will continue the NHERI Lehigh Seminar Series down the road at some point, and hope everyone has a great evening. Take care.
Wonderful. Thank you.